Hi guys, I'm Dana from Period 1 and today I'll be talking about how to apply derivatives to real life. So the first real life example is about displacement, velocity and acceleration. So displacement is the distance and the direction an object has moved from an origin over a period of time, and it is represented by s of t. Velocity is the rate of change of displacement of an object with respect to time, and it is represented by v of t. Acceleration is the rate of change of velocity with respect to time, and it is represented by a of t. In general, to find the velocity, you take the first derivative of displacement. To find acceleration, you take the first derivative of velocity. In other words, you can also find acceleration by taking the second derivative of displacement. Let's jump right into the first example. The first example says, a particle moves along a straight line with the equation of motion s equals to 1/3 t cubed minus 2t squared plus 3t, where t is more than or equal to 0. In part A, we are asked to determine the particle's velocity and acceleration at any time t. To go about doing this, we have to differentiate the function of s to get the velocity and differentiate it again to get the function of acceleration. When we differentiate s, we get t squared minus 4t plus 3. When we differentiate s again, which is just differentiating velocity, we get the equation of acceleration, which is equal to 2t minus 4. And with that, part A is done. Now, let's look at part B, which says, when does the motion of the particle change direction? When dealing with change of direction, we equate velocity to 0. Since v is written in a quadratic equation, we factorize them to get the answer easily. As a result, we get t minus 3 times t minus 1 equals 0 and t equals to 3 and 1 respectively. Thus, the direction of the motion of object changes at t equals 1 and t equals 3. For part C, initial position would mean displacement equals 0. When we simplify, we will get t cubed minus 6t squared plus 9t. After further simplification, we will get t times t minus 3 to the power of 2. Thus, t equals 0 or t equals to 3. We have now completed the first application. Let's move on to the next. Now, we'll be looking at the second application, which is finding maximum and minimum values on an interval. So let's take a look at this graph with points A, B, C, D and identify the absolute and relative extreme values of this graph. The absolute maximum is the highest point of the graph. The absolute minimum is the lowest point of the graph. Now, this peak right here is not the highest point, but is the highest point in this local area. So it is called the local max, aka relative maximum. This point is a relative minimum. To identify the location of absolute extrema, you need to compare the y values, so a data table would be useful. To identify the relative extrema, you need to identify the locations where the slope is 0. Since we have a horizontal tangent line, f prime of b will be equal to 0 and f prime of c will also be equal to 0. Now, let's work on a practice problem. Let's say that f of x is equal to x squared minus 4x plus 9 and identify any absolute and relative extreme values of the function in the interval between 1 and 4. Firstly, identify the critical points. That's when the first derivative is equal to 0. When we take first derivative of f of x, we get 2x minus 4. When the first derivative is equal to 0, x equals 2. To determine whether this is a relative min or max, we plug in values from the left and right of 2 and see if the sign changes from left to right. When x equals 1, f prime of x is a negative value, so the slope goes down. When x equals to 3, f prime of x is a positive value, so the slope goes up. If it changes from negative to positive, it is a minimum. Thus, where x equals to 2, there is a relative minimum. Let's move on to the absolute extreme value. Once you have all of the critical points, make a table. In the table, put the endpoints of the interval and in between that, the critical points. Now, substitute the values into f of x and get the y value. Notice that 9 is the highest y value, therefore it is the absolute maximum of the function. 5 is the absolute minimum value because 5 is less than 6 and 9. In addition, it is also the relative minimum. So that's how you could find the absolute and relative extreme values. Now, let's move on to the final real-life application of derivatives. Congrats on making it to the final example of real-life application of derivative, which is optimization problem in economics. I'll be showing how to solve the problem in 4 simple steps. Let's hop right into the first example. The first example says a commuter train carries 2,000 passengers daily from a suburb into a large city. The cost to ride the train is $7 per person. Market research showed that 40 fewer people will ride the train for each 10-cent increase in the fare and 40 more people will ride the train for each 10-cent decrease. If the capacity of the train is 2,600 passengers and carrying fewer than 1,600 passengers means cost exceeds revenue, what fare should the railway charge to get the largest possible revenue? Right now, the revenue is 2,000 times $7, which is $14,000. To calculate largest possible revenue, we let x represent the number of 10-cent decreases in the fare. Then we can write the expressions for both the number of passengers and the fare per passenger as follows. Price equals to 7 minus 0.1x and tickets equals to 2,000 plus 40x. Alternatively, we can also let x represent the number of 10-cent increases in the fare, where the expression will look like this. Price equals to 7 plus 0.1x and tickets equals to 2,000 minus 40x. We will continue using the equations from scenario 1. We know that revenue equals to tickets multiplied with price, so the equation is as follows. After expanding and simplifying, we should get negative 4x squared plus 80x plus 14,000. Next, we have to get maximum revenue, where we let the derivative of r of x equals to 0. Upon simplifying, we will get x equals 10. Finally, all we have to do is substitute x back into the individual equations and r of x, which we will find that the new price is $6, the new amount of tickets are 2,400, and the new revenue is $14,400. That is all for the application of derivatives to real life. I hope you enjoyed my video and take on the application of derivatives.